Okay, so here's a question from matrix algebra. It says, for which real numbers A and B is the transformation from the plane to the plane with this particular configuration orthogonal? Okay, so we have no idea what A and B are. So we may gain some information by making the assumption that the transformation involved is indeed orthogonal. So first, that T is orthogonal. What does that mean? That means that it preserves length. So in other words, for each x and y real, we have that the norm of x and y is equal to the norm of the transformation applied on x and y. Okay, so in particular, for x equal to 1 and y equal to 0, we have that the norm of 1, 0, interpret this as a vector, is equal to the norm of the transformation applied at 1, 0. But what is the norm of that? Well, this is nothing else but a times 1 in the first coordinate, or in the first entry, as you want to interpret it. So a for the first, then minus b times 0, so that is just 0. So what remains is a. So now what about the second entry, or the second component of the vector? That would be b times 1, so b, then plus a times 0, so that is just that. But if we examine this, it's probably a better idea to introduce the squares. That way we don't have to deal with the square root. Well, what does that mean? This means then the norm of this one is just 1. So this is 1 is equal to a squared plus b squared. Okay. So just based on this observation, we obtain an equation that relates a and b. Then you say, well, is this all that we need? In other words, if we make the assumption that this equation is being established, holds actually, do we get that we indeed get a linear transformation that is orthogonal? So there is a linear transformation. Well, there's no doubt. Simply look at the expressions here, are linear combinations of these entities. The question is the orthogonality. So let's see if this condition also works in the other direction. So let's assume that a squared plus b squared is equal to 1. Let x and y be real numbers. Then what we're going to do is make an exploration about the norm of the transformation. And once again, we're going to make it in such a way that we don't have to examine the square roots. So I'm going to square them. So now from here, I'm going to say the following. Well, what is this? Well, not much that I can do. This has to do, or this has to be, I'm sorry, with just copying that. So ax minus by, comma, bx plus ay. Of course, squared, right? But then from here, well, Pythagorean theorem, we're going to do is square this and add them. So I have the following expression: ax minus by squared plus bx plus ay squared. Now, this is just a binomial that we have to expand. So it's a squared x squared minus, well, 2abxy. Right? You can do some algebra and verify that this is indeed the case. Plus b squared y squared. Now, what do we get from this side? Well, we get plus b squared x squared plus 2abxy plus a squared x squared. But you see, now these two terms are identical but with different signs, so they cancel each other. And now, look, we have a squared x squared. Sorry, this should be y. minor mistake, but very important. So you have a squared x squared, you have a squared y squared, so we may factor this. But now also the same happens with b. So I have b squared times y squared from here and from x. That means that I can rewrite this in these terms, a squared plus b squared times x squared plus y squared. But then look, I made the assumption that this is 1. So this is 1 times x squared plus y squared, which is nothing else but the norm squared of xy. So the condition that we have here, that a squared plus b squared equal to 1, is necessary and sufficient for this to be an orthogonal.